Good evening, students. So, I am back again with a small video lecture on some important differences that are there. So, it will be a short video again, just a common bit of knowledge with regards to some other common terms that we use. Okay, so as you can see over here, the first point that we will be discussing will be center of gravity, which is also, written in the short as C dot G, which we are very familiar with, at least with the term, if not the exact actual knowledge of it. So, center of gravity versus center of buoyancy. Okay, now this, if you can, call this as C dot B. There's no universally accepted rule for this like we have for CG, but we will understand the difference between these two terms. But before going to the difference, we must understand the process of buoyancy. Okay, so if you have really studied fluid pressure and things which are immersed, the solid things being immersed in a fluid, you will probably have understood what buoyancy is. Buoyancy is, the upward force acting on an immersed body. Now this is, I'll give you a brief understanding of the word buoyancy. Whenever you dip or try to dip a particular solid shape or a particular solid which may be hollow or it may be, fully solid, if you try to immerse it in a fluid, not necessarily a liquid, it can be a gas also. That is why I'm using the term fluid. So fluid would mean liquid plus gas as well. So if you are dipping some solid body in a liquid or in a gas, you will feel that there is an upward resistive force that your hand is experiencing. So your hand is trying to push thing down, but your hand is actually feeling that there is somebody who is doing the opposite thing, like who is resisting that push down. So that is basically being done by the displaced water or the displaced liquid, which has actually, it has been displaced because your solid body is going into that particular liquid. So liquid occupies all the space. For your solid body to go in, the liquid has to move, liquid has to make way for that particular solid body to occupy space. Okay, so it is a result of that there is a upward thrust or upward force which acts on the body. This is known as the buoyant force and the process is known as buoyancy. Okay, so that is the rough idea that we have about buoyancy. Now let us go to the difference of center of gravity and center of buoyancy. So let me just draw a diagram to show and explain to you the difference. So let's say that we have this particular container, let's say for example. Okay, so I'm going to show this as a container filled with some kind of a liquid. Okay, so this is the idea. Okay, now supposing that I take a solid body like this, a solid body like this, in which there is a uniform mass distribution. Okay, so it's like you can consider this cubical or a cuboid kind of a body which is fully solid from inside. Okay, so the center of gravity will be somewhere right in the middle at the center. So you can say that this is the CG point or the center of gravity. So what is center of gravity? For a uniformly shaped body, the center of gravity is a point on the body. It may be outside the body also. So it's a point on the body or outside the body where the entire weight of the constituent particles of that body acts. Okay, so you can imagine that this particular big sized body will be comprising of a number of small particles of mass. Okay, millions and trillions of particles of some mass or the other distributed throughout the body. Okay, and it is exactly how this entire body gets constituted. Okay, so it constitutes a number of small particles of small masses. Okay, so when you put them together, you get this shaped body or this sized body, and right at the center you have the center of gravity. Remember, the condition is that the mass should be uniformly distributed throughout. Okay, so this is your center of gravity. Now let me introduce the term center of buoyancy also. So let us say that we have the same body. So let me just draw that body again, but this time with a small difference. So you see, the idea here is this. So it is only this portion of the body which is below the water surface, okay, or below the liquid surface. Okay, so this is a situation in which that same cuboidal or a cube shaped body of uniform mass has been immersed, not fully but partially, in water. Okay, so now you see the difference between the center of gravity and center of buoyancy. Center of gravity, as we discussed, will always be acting at the center, the geometrical center, because this is a regular shaped figure having uniform mass distribution. So the middle point or the center point geometrically will be somewhere here, which will be slightly above the surface of water, because remember, we have not dipped the body fully or even half. Only some portion of the body is below water and the maximum portion is above water. So let me make this a little more clearer so that you understand it more clearly. So let's say, for example, we have a situation like this, something like this. So this is the figure that I am talking about. Okay, so essentially what I have done is, you can take any shaped body, that's not a problem. The reason why I have shown you a figure like this is because I actually had to show that there is only a little bit of a portion of the entire body below water and majority of the portion is above the water or above the liquid. So again, coming back to the difference between center of gravity and center of buoyancy. Center of gravity will always lie at the geometrical center. Okay, so let me use a black colored marker to show you this. This will be the geometrical center of the entire body because of the shape. So you have this as center of gravity. Okay, but is it necessary, is it necessary that the center of buoyancy also will remain over here? No, not in this particular case, because you see, center of buoyancy is actually the midpoint or the geometrical center of only that portion of the body which is below the liquid. Okay, so for center of buoyancy, you really don't have to worry about the portion which is above the surface of water. So the only point of concern will be the portion below the surface, and for that the midpoint will be somewhere here. So you will call this as center of buoyancy. So although you see that they are acting in the same straight line, okay, if you draw a hypothetical kind of a dotted line passing through this particular center of gravity, you will find that the center of buoyancy also falls on the same line. But is it exactly falling on the center of gravity? Is the point of the center of buoyancy falling exactly on center of gravity? No, not in this particular situation, although you still can have a situation in which they both overlap. So I'll show you this in the same diagram. Let's say, for example, that you dip this particular liquid, dip this particular solid body, so that you have exactly half of the portion, let's say only this much portion. So let's suppose that this is the situation now. Okay, now this is the situation where you have liquid all through over here. Now you can see that this body has been immersed so that half of it is below water and half is above water. Okay, so that this line of demarcation is lying exactly at the middle height. Okay, so certainly when you will talk about the center of gravity, the center of gravity will lie at the geometrical center, like we discussed it for this body also. Similarly for this body also, it will be at the geometrical center, and this time because we have dipped it half below water, so you will have the center of gravity here. Okay, which is exactly at this point. But where will the center of buoyancy be? Center of buoyancy again will be at the midpoint of only the immersed portion. So the immersed portion midpoint will be somewhere here. So in this diagram also you can see that center of buoyancy, if I write that as C dot B, center of buoyancy and center of gravity, they are lying although in the same straight line, but they are at different points. So as long as you can see, as long as you have partially immersed bodies, center of gravity and center of buoyancy will never be at the same point. Okay, now I'll show you a case where the full body is immersed or the entire body is immersed. Now look at this particular case in which you can see that the entire cuboidal or the cube shaped solid body has been fully immersed under the surface of water or the liquid. Okay, now you see the water or the liquid is actually, you can assume, although this is not a hollow body where through which the water can enter the body, but you can assume that it is fully immersed. Okay, now in this case again the center of gravity, because of the geometry, the uniform geometry of the block, you can see that it will be at the geometrical center. Okay, but this time the center of buoyancy, because the full body is immersed, so according to the definition, what is the center of buoyancy? It is the middle point or the central point of the portion of the body which is immersed. But this time, in this particular situation, whole body is immersed, so the midpoint of the immersed portion will also come at this point, which will be called as center of buoyancy. So this is the only case in which you will have the center of gravity as well as center of buoyancy lying at the same point, because the body is fully immersed under the surface. So I hope you have understood the difference between center of gravity and center of buoyancy. Now we are going to go to different difference, let's say, and it will again have the word center of gravity, but it will be compared this time with center of mass. Okay, so let's say we have center of mass versus center of gravity. Okay, so again, although this is the term that is more commonly used, we usually neglect center of mass, but we must understand the difference. Now for understanding the difference between the two, let us take an example where we have a body, a uniformly distributed mass in a body which is quite long. Let's say, for example, okay, so here is the diagram that will help you understand the difference between center of mass and center of gravity. Now let's talk about center of mass first. Okay, so center of mass is a point on the body which is the midpoint, or you can say that it is the central point with regards to the continuous mass distribution or the uniform mass distribution on the body. So let us take an example to understand this. Suppose this is a very very big bar of aluminium or copper or any metal, or let's say even a wooden kind of a material. Okay, the main point here is that the body or the long rod or the long uniformly shaped body that we have same mass distributed throughout the body. So that means that the thickness over here The thickness over here, the density of the material over here, the density of the material over here and here. Throughout the body, there is uniform density of the material or the mass packed inside. Okay, so no part of this long rod is thicker than another. No part of this rod has more density than any other part of the rod. Okay, so it is that condition that we are taking into play. So certainly the center of mass will lie at the exact midpoint, which will be somewhere at the middle of this particular rod. So we can say that this point is the center of mass. Okay, so this is the center of mass. Now did acceleration due to gravity actually play a role in deciding the center of mass? No. The answer is no, because as the name suggests, it is center of mass. As long as the mass is uniformly distributed throughout the body, we can easily say that half of the mass is to the left side and half of the mass of the rod is to the right side. Therefore, we have achieved the geometrical center, which is known as the center of mass of the body. Now, talking about center of gravity of the body. Now, the moment we say gravity, what comes into play? Weight comes into play. Okay, the weight of the body comes into play, and whenever we say weight of the body does not only depend upon mass, it is actually a product of m and g. Okay, so now this will actually help you in understanding the difference between center of mass and center of gravity. Center of mass is only going to be dependent upon the mass distribution, not on the gravitational pull. Okay, so no matter whether you take this rod here on the north pole, at the equator, slightly tilted, whichever way you want to take the rod, whichever place you want to take the rod, the center of mass is going to be same, because it is not dependent on gravity. Now coming to again back to center of gravity, which depends upon weight, which indirectly again depends upon two things, mass and gravity. So we understand that although mass is uniformly distributed throughout, is g same throughout the position of the rod? What I mean to say is, if you consider this point over here, which is near the equator, and you consider some point over here which is near the pole, in fact exactly at the pole, do you think that g value here and the g value here would be same? No. G value in fact is maximum over here, and the value of g over here is 10 meter per second square, whereas this over here at the equator, near the equator, it is slightly lesser. So you can say, let's say for example 9.8 meter per second square. Okay, so it is because of this difference we say that although mass is uniformly distributed, but the effect of gravity that is there on different parts of the rod is going to be different in different places, because we all know that this rod is so huge, so big, that it is actually covering the north pole as well as the equator, reaching the equator also. Okay, so can you now say that the center of gravity will also lie exactly at the center, just like the center of mass? No. So it would be wise to say that the center of gravity will be tilted towards this side, which is the side which is facing the north pole. Why? Because to this side we have more gravity or more gravitational pull in comparison to this side, because this side is closer to equator, whereas this side of the rod is closer to the pole where g is more. Therefore your center of gravity may lie somewhere here. Okay, so the center of gravity of the body in this particular case may be somewhere here. So naturally this only comes into significance, or this only gets significant when we are considering an extremely large shaped body, an extremely large sized body rather, okay, which is actually covering a number of areas where there are different acceleration due to gravity. Okay, where there is different gravitational pull, where the amount of gravitational pull or the strength of the gravitational pull is different. Naturally, if you will take only a small scale right at the center over here at the equator, right at the center, so the center of mass and the center of gravity both will be at the same point, which is the geometrical center of the scale. Why? Because the place where you are keeping the small scale, it is a place where the acceleration due to gravity remains same, it doesn't change. You see, you can't say that, once you are standing over here, gravitational acceleration due to gravity is different, and you take 10 steps to the right and gravitational pull becomes different. No, gravity only changes, or the gravitational pull strength only changes when you cover thousands of kilometers, or let's say hundreds of kilometers towards the poles. Okay, it is only then that there is a minor change in gravitational pull, which actually creates a different center of gravity. Okay, so that is the idea, or rather that is the difference between center of mass and center of gravity.